Linear versus exponential functions. You've been working a lot this year with linear functions. So as a reminder, remember that a linear function takes the form of y equals delta x plus f of 0, or y equals mx plus b. So for example, if I take y equals 2/3 x minus 2, we remember that this piece on the back end is our y-intercept. So starting down here at -2, pretty close to -2, and remembering that this piece right here represents your slope, or what we need to remember is also called rate of change. That's important for this unit. And so that rate of change says we're going to go ahead and go up by 2 and over by 3, over by 2, up by 2 and over by 3, and then we can connect those to draw a line. So remember that we've got the rate of change, we've got the y-intercept, because those things are going to come up again many times in this unit. Today we're going to start getting into the idea of exponential functions. Just like linear, they do still have a y-intercept. They also will still have a rate of change. However, theirs looks more like this. Theirs will say y is equal to f of 0 times delta raised to the x power, or y equals a times b to the x. In this case, what we're looking at is f of 0, just like with linear, is still your y-intercept. Delta is still your rate of change. So the pieces are the same, they just are going to look a little different when we end up taking care of them. I'd like you to follow along and do a paper cutting activity. So start with one piece of paper. When you start with one piece of paper, you have made 0 cuts. Now fold the paper in half and cut it. You've made 1 cut. Think about now the fact that you have 2 pieces of paper. Stack those pieces of paper, fold it in half again, and make another cut. Now you've made a total of 2 cuts. How many pieces of paper do you have? You should have 4. One more time. Stack them, fold them in half, cut them. You made your 3rd cut. Count up your pieces of paper. You should have 8. Let's take a look at what that looks like on the graph. So now what I've got is I want to think about the fact that I was at 0, 1, we were at 1, 2, we were at 2, 4, and we were at 3, 8. When I connect these dots, we don't get a line, we get a curve. And this is what an exponential function looks like. One of the things we need to keep in mind in this unit is the idea of growth versus decay. So in this case, a growth graph does this, and a decay graph does this. In this case, I want you to think multiply. In this case, I want you to think divide. Let's look at the tables for both types of functions. In a linear function, we know that over here we increase by 1 each time. On the exponential side, we're going to see the same thing. I increase by 1, so in this case they're the same. But now I want to take a look at what happens in the y column. In this particular linear function, I'm adding 2, and adding 2, and adding 2. So our common ratio, or our rate of change, or our delta, is equal to 2. In the other one, here I could think of as a plus 1, but when I go from here, it's not a plus 1. So that's not what we're looking for. 1 to 2 can be times 2, 2 to 4 is times 2, and 4 to 8 is times 2. So here, our delta, our rate of change, is a multiply by 2, and we call this a common ratio. So you'll hear us refer to this as a common ratio more than rate of change for this unit. Let's look at the graphs. Here, we need to think about the idea that graph, a linear graph, is just what it says. It's a line. So I can put that line in here, and I can make it an increasing line, or I can make it a decreasing line. But all in all, it is a line. For the exponential graph, there's always a curve. For a growth graph, this is going to start right along here. It's never going to cross that axis, and it'll gradually start to go up forever. Important thing to remember is that back here, that white arrow will get very, very, very close to the x-axis, but it will never go across it. Let's look at their equations. This will be the final thing we'll look at for this video. We said in the beginning that a linear takes the form of y equals delta x plus f of 0, and the fact that your delta was your rate of change, in our case we called this slope, and your f of 0 was your y-intercept. Same thing happens on the other side. I still have f of 0 as a y-intercept. I still have a delta piece. It is still my rate of change. But remember, we're going to call that a common ratio. Also notice here that the x becomes an exponent for the exponential. The other format we saw, remember, here was y equals mx plus b. On the exponential side, we will see the one I have given, as well as y equals a times b raised to the x, where a becomes the y-intercept and b becomes your rate of change.